Okay, so let's talk about the Euler totient function. Another important name is the Euler phi function. Sometimes it is even written as this, and here it is phi of something. You can see it right over here. So let's call it like O because phi is hard to write. So what it gives me, a number of the number of integers that are relatively prime to n from 1 to n. So this, maybe we'll make a header of Euler totient function, also called Euler's phi function. Let's just close the door here. Okay, so we're going to talk about this one. And again, the idea is to give me the number of relatively prime numbers from 1 to n, of a number of n. So I give it a number n, and it gives me back the number of relatively prime numbers to n from 1 to n. For example, if I have, for example, 12, we have 4 prime numbers that are relatively to 12 that are from 1 to n. Let's count them. So we have 1. It means that the GCD of n and this number is 1. So let's count it. We have 1, which of course it is relatively prime to 12 because it only has a greater common divisor of 1. Now 2 is not, 3 is not, 4 is not, 5, yes, I think it is. 6 is not because they have greatest common divisor of 6. And 7, yes. 7, yes. 8, no, because they have greatest common divisor of 4. 9, yes, 9 is good. 10, no, 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 because 9 I have 3 that can divide both. So 9 is not good. 10 also not good because 2 of course divides both. 11, yes, because only 1 divides 11 and 12. And what about 12 itself? Of course not. So here are the 4 relatively prime numbers to 12 because they have greatest common divisor of 1. I mean, if you are doing greater common divisor, you're looking for the greater common divisor of 1 and 12. You get 1 greater common divisor of 5, or let's 12 and 5 is also 1, but for example, greater common divisor of 12 and I don't know 6 is 6. So I think it is, right? You can say this. Let's ask ChatGPT if I'm just right. Greatest common divisor of 12 and 6. Let's see that I'm not doing any mistake here. Yes, it's 6. So you get this. The Euler phi functions give me the number of relatively prime numbers from 1 to this number, and that's it. So let's see how we can calculate it, because it's not very easy to do what I did, right? Going from one number to the other. Think of it if you need to calculate the phi number of, let's calculate now 1, it's yes, 2, maybe yes, maybe no, 3, blah, 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 blah. What we can do, there are formulas. This is the definition, very important definition for the phi function. You see that it is the number, phi n is the number of k's in 1 until n such that the greatest common divisor of this k and n is 1. So we are just counting, and this is for counting. This is this one here, and this one here is the size of, the number of. So we are counting what is the size, what is the number of elements in this group, the group that contains all the numbers that are relatively prime to n, and the number of elements in this group, this is the phi function. So how we can calculate it? We can do a brute force, let's call it, like I did, checking one number after the other from 1 to n. Or we can use the formula that you can see right over there. Calculate, I don't know. So first formula can be if n is a prime number to the power of some integer, right? Where p is a prime number, then I think they're meaning that k is a integer. In this formula, in phi function, the k is an integer. I wish you would get what I say. Yes, in the formula, yes, k is a positive integer. So if I can represent my n that I want to calculate the phi function for as a prime number to the power of some positive integer, so I can say that the formula that I can use is just this formula, which means that the phi of n is just my p to the power of k minus my p to the power of k minus 1, which you can take off p to the power of k and get 1 minus, let's call it p to the power of minus 1 instead of dividing, because not all the time we can divide in everything. Okay, so this is if I can present the n as a power of some prime number. Another case is the general case where I can factor my n if I can present as its factorization. For example, 12 can be factorized to 2 to the power of 2 times 3, right? This is the factorization of n of a 12. So I can do this formula, which you can see right over here, which is this one, which is phi n equals. Now, this is the n, 1 minus p1 to the power of minus 1. Again, it's if I can factorize n like this thing, I can factorize n as a multiplication of prime numbers p1 to the power of e1 times p2 to the power of p2, and etc., pm to the power of em. If I can, this is the general case, it's factorization of a number, and then I can use this formula to calculate what is the Euler phi function, or if you want to call it, totient function. So I take n times 1 minus, like you can see here, 1 minus p1 to the power of minus 1 times 1 minus p2 to the power of minus 1, and etc., until 1 minus pm to the power of minus 1. Okay, this is the Euler phi function. Now, if I take the Euler phi function of 12, we can see an example. I can factorize 12 as I said before, 3 to the power of 2, 2 to the power of 2, which is 4 times 3. Now I can do the formula, which is O of 12 equals 12, my number, times, and I don't really care about the power, but I do just 1 minus a half times 1 minus a third. And what I get is 12 times half times 2/3, right? Which when you calculate it, you get 12 times, oops, 12 times just third, which is 4. So as you can see, we got what I just calculated brute forcefully. I got that the phi function of 12 is 4, namely there are 4 relatively prime numbers from 1 to 12, and this is it. You can see here another example for 30. Again, it factorized for its factorization, prime factorization of this number. Again, prime factorization. You can see that all the numbers here are prime, and you can see the result. And there are some properties for the phi function. So if I say properties, now we have the first property, which is the phi function of a and b is the phi function of a times the phi function of b. Another property is the phi function of a number is less than or equal to the number minus 1, because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I mean, except for this, sometimes except for its own number, all the numbers are prime, relatively prime to this. For example, I can think about, for example, prime number. Think about the phi function of a prime number. It can only be divided by a 1 in itself. So the number of prime numbers, relatively prime numbers to this number is, for example, 7. 1, 2, 3, 4, 5, 6, 7, no, not including itself, so until 6. For the prime number of 7, for example, it should be 6. So let's just see that I'm not making any mistakes. So what is the phi function, maybe of 7, for example? So I want to see 6. Yes, as you can see here, it's 6 because it's a prime number. So for a prime number, maybe this is not written, but maybe for prime numbers, I can say that the phi function, phi of n, equals n minus 1. So if n is prime, the phi of n equals n minus 1. Maybe this is a general rule that I can say. Yes, that's correct. So it's quite nice. Let's continue. Not here, it's here. And Euler theorem, if a and n are relatively prime, then or I can say that a to the power of phi of n, and a and n are relatively prime, so it equals 1 in modulo of n. Another property of the totient function, Euler's totient function. Okay, so this is the idea of Euler totient function, or if you want, Euler's phi function. The number of relatively prime numbers to a number. We have two options. If it is a power of a prime number, you can calculate straight this one. If it's not a prime, if it's not a, it's very interesting. Think about it. If I have, just for example, if I have a prime number, I mean, if n is a prime number itself, for example, 7, so it's a prime number time to the power of 1, so all of this 7 equals, so now my k, it means that my k is 1, right? Because it's the 7 to the power of 1. So it's the prime number to the power of 1 minus the prime number to the power of 0. So it's 7 minus 1, so again, it's 6. So if I have n prime number, so this formula comes as n equals n to the power of 1, and therefore the phi of n equals n to the power of 1 minus n to the power of 0, which is n minus 1, which is what we just said right over here, which is the phi of n if n is prime is just n minus 1. Quite nice, quite nice. Okay, but this is the first formula. If the n is a power of a prime number, if in a general case, namely it's not just a power of a prime number, it can be, but it's not have to, so I can do the prime factorization of the number, and by that using this formula, or maybe more commonly, more convenient to see like this, with latex, this formula to calculate the phi function of the number. Thank you very much. And we talked about the properties of the phi function. Thank you very much. If there are mistakes or correction or hallucination, please tell me. Thank you very much. And that's about the Euler's totient function or Euler's phi function. Thanks.